Good afternoon, everyone. My name is Albert Cabin, and it is an honor to present the research entitled Experimental Testing of Solid-Fired Clay Bricks in Compression, Comparison of Different Bearing Surface Treatments. This study has been carried out in collaboration with Lou Capella and Per Roca, and forms part of a wider research agenda dedicated to enhancing mechanical characterization techniques for masonry units, particularly within the context of heritage and existing construction. Brick masonry remains one of the most widespread structural systems worldwide, used in both modern buildings and historical heritage. The structural performance of masonry relies heavily on the mechanical properties of its components, primarily bricks and mortar. However, there is still a significant lack of consensus in current standards regarding the appropriate testing methodologies for these materials. Most existing norms focus on new construction, offering limited guidance for characterizing materials from existing buildings. This creates a challenge, especially in heritage conservation, where the ability to reliably assess existing materials is critical. Our aim, therefore, is to contribute to the development and validation of standardized protocols for testing solid-fired clay bricks, with particular attention to their compressive behavior. The central objective of this work is to improve the experimental knowledge related to destructive testing methodologies used for evaluating the compressive strength of solid-fired clay bricks. The study seeks to evaluate both traditionally handmade and industrially extruded bricks. In doing so, we aim to explore how specimen shape, size, surface treatment, and stacking influence test results, and to ultimately identify procedures that deliver reliable, repeatable outcomes. The experimental campaign involved a collection of materials from buildings constructed across different time periods, ranging from mid-19th century residences to early 20th century industrial and market buildings. These represent a broad cross-section of Barcelona's architectural heritage, ensuring that the results reflect a diverse set of real-world masonry units. The research addresses a wide set of experimental variables. These include the influence of material anisotropy, the stacking configuration of specimens, the header-to-stretcher orientation ratio, specimen slenderness, and the surface treatment applied to the loading areas. Each of these parameters has a known or suspected effect on the apparent compressive strength obtained from tests, and must be rigorously studied to ensure validity. Our compressive strength analysis considers 5 key variables: the size of the specimen, whether units are tested stacked or unstacked, the orientation of the brick header versus stretcher, the slenderness ratio of the sample, and the treatment of the loading surface during testing. All of these parameters are studied systematically for both extruded and handmade bricks. A particular focus of the study was the evaluation of various surface treatments on the brick loading faces. The options considered include grinding, cement and gypsum capping, placement on plywood or fiberboard, a thin layer of gypsum powder, and, most innovatively, the use of oil PTFE sheets. Each treatment was applied to different specimen sizes, including standard 100-140 in cubic meters prisms, 40-40 mm cubes, and half or whole bricks. The campaign compared results from standard specimens defined in N770-1 and N12390-1 with those from non-standard smaller cubes. Our aim was to assess whether the reduced size specimens more suitable for sampling in heritage structures could yield reliable compressive strength data. Failure patterns were documented in accordance with N12390-3. These visual and mechanical observations help to assess how variations in loading and specimen configuration influence the stress distribution and fracture propagation within the brick units. A detailed comparison was conducted between standard-sized and 40 mm cubic specimens. The ratio of strengths FC 100 FC 40 was calculated, with accompanying data on average values, standard deviation, and fifth percentiles. The results suggest that despite some expected reductions in absolute strength, the smaller specimens can offer statistically representative results. We documented all specimen configurations used throughout the study. These include combinations of size, orientation, slenderness, and loading surface treatment. This comprehensive matrix ensures the robustness of our comparisons and supports reproducibility. Stacked specimens, especially those with low slenderness, often yield higher compressive strengths due to confinement effects. Our data showed this consistently across both handmade and extruded bricks, in both header and stretcher orientations. When comparing compressive strength values of half versus whole bricks, we observed a clear ratio trend, with full units generally yielding higher strengths. This is particularly relevant when considering practical constraints in sample extraction from existing structures. The influence of specimen slenderness on compressive strength was explored, following the theoretical basis established in Van Meyer's work 1984. Increased slenderness generally leads to reduced lateral confinement and thus more conservative strength estimations. Slenderness effects were observed to differ depending on the brick manufacturing process. Handmade bricks, which often have greater variability in density and texture, showed less regular behavior than their extruded counterparts, where the effects were more predictable. The use of oil PTFE sheets significantly reduced friction at the loading interfaces, yielding compressive strength values that were notably consistent, regardless of specimen shape. For extruded bricks, an average of 34.3 megapascals was recorded, 10.4% coefficient of variation, and for handmade bricks, 9.5 MPa, 20.2% COV. This suggests PTFE is a promising candidate for future standardization. The combined results for extruded and handmade bricks are presented here, including statistical aggregates for each configuration. This offers a complete overview of how variables interact and influence compressive strength outcomes. Our findings reveal that different international standards can lead to significantly divergent compressive strength values. While ASTM and CAN-CSA tend to overestimate, the Australian AS and ZS standard is generally more conservative. The incorporation of PTFE sheets appears to offer a repeatable and relatively unbiased surface treatment method. Although slightly conservative in strength, it enhances test consistency. We recommend further studies to explore its adoption in practical testing protocols for both laboratory and on-site applications. Thank you for your attention. We believe this study offers valuable contributions towards harmonizing experimental protocols for brick characterization and opens avenues for more refined, standardized approaches to evaluating existing masonry. I welcome any questions you may have.